destroying all the forest. So this is also useful in the forest fire or the wave fronts for a light or a high frequency sound wave or a sonic. Uh, uh, Roberto, would you please turn off your mic?
Oh,
Yeah, thank you. So, if you will take a look and the sun rays in the morning comes on the earth, so what happens? Of a wave front like a leading edge is propagating and then it comes to the earth. So the propagation speed is so high that we cannot analyze with our eyes, with our eye norms. We cannot analyze how they are propagating because the propagation speed of the light, sunlight basically, sunlight is so high that we cannot analyze how it is coming. We see that it comes from the sun, so a, a wave front which is leading this race. And also there is a velocity, the velocity c, with this velocity the wave front is propagating. So what is the velocity of light? Can anyone tell me? What is the velocity of light?
um, 300.000 kilómetros por segundo.
Sorry, here it comes 3 or something else.
Ok, sí. A metros por segundo, sí.
Can you please repeat?
Ah,
So it is something like equivalent to 3 into 10 to the power 8. So this velocity is so high
ok.
that when it is leading that light rays, we won't be able to analyze how it is coming. However, if the wind is coming, if the wind start to flow, like if you can see how to storm, if you see the storm and the wave front of the storm when it starts to come, so it can be felt because the velocity of a storm for sure will be less than the velocity of the speed of light with the light. So when a star start to come towards us, then we can see the leading edge, but for the light we cannot see, but also it is following the same thing, it is also following the same thing. So this is the optics where this Econel equation is used, where the wavefront is started to propagate and these does not intersect. It is our assumption. Or the shock wave generated by a so supernova explosion. So basically, if there is a reacting particle, there is a reacting gas which is filled in, like suppose atom bomb. So what happens? What happens in this atom bomb? Suppose this is the atom bomb. When when it blast, so the movement, that shock velocity. So what is the meaning of the shock velocity? There is a velocity whose, there is a disturbance, there is a disturbance whose velocity is much greater than the velocity of the air. So when this atom bomb blast, it also expand in the terms of the fire, and also there is a velocity, there is a disturbance which propagates with a very higher velocity, so it starts to destroy the nearby things. So what happens first, this is the leading edge, and then it starts to propagate. So that is the supernova explosion. Explosion. So you can see that this kind of wavefront propagation has application in forest fire, for wavefronts for a light or a high frequency sound wave, sonic boom, shock wave generated by a supernova explosion, sonic boom generated by a jet plane. As I told you, when the jet plane start to fly, the nearby surrounding, in the nearby surrounding, there is a disturbance whose velocity is much
Kilometers.
greater than the velocity of the air. Now if you are not getting very clearly what I am saying, then I have also uploaded the notes in the Google Classroom, so you don't need to focus a lot. And sorry, uh, I cannot turn on the camera because there is no electricity. So these cases differ by how the velocity c of the wavefront, velocity c is determined. Now here we will only consider the situation. Here we will only consider the situations where the velocity is function of the direction, like the space variable is a reasonable approximation. Why it is so? Just think in your mind, just think in your mind, when a storm comes, so initially the velocity is very high. Suppose this is the wavefront of the storm. So initially the velocity is very high. But as soon as it travels a distance, the velocity will start to be
300,000,
reduced. Is not it? When a storm
300,000.
start initially the velocity is going
300,000,
to be very high, but as soon as it propagates with respect to distance, the velocity is going to decrease. The
300,000
velocity is going
kilometers,
to decrease with the distance
300,000
it is covering.
300,000 kilometers,
So
kilometers.
here the velocity as a function of space variable is a reasonable approximation, because if you are considering the fire in, suppose the fire in Amazon forest, so as soon as it covers a distance, the leading fire, the velocity of the leading fire is going to decrease. So front speed almost always depends on more factors. Even it depends on time than just location. This is the location, so it also depends on other factor, but most researcher, a lot of researcher has find that this is a very good approximation, but this is a good approximation in many cases. As long as the wave fronts do not self-intersect, we can describe them via a phase function phi. The case which I was taking, that the wave front, we are considering that the wave fronts are not intersecting. It is just our assumption. So as long as the wave fronts do not self intersect, we can describe them via a phase function phi defined by phi of x equals to t if and only if this location is belonging to wave front at time t. Thus it should be phi vector x plus c. It is propagating in the normal direction of the wavefront itself, so it is going to be phi x plus d of t, where n cap is the unit normal to the wavefront at location x. Now just explain the left hand side of this equation and you will be getting some terms will be cancelled out with the right hand side and you will be getting c and gradient of phi is equals to 1. That is, it can also just square both sides. C square gradient of phi square equals to 1. Where the second equation follows from, we are taking gradient n cap is gradient of phi over. So this is, we know that if a wave front phi is propagating, then its unit normal is gradient of phi over the modulus value. So this is coming, the normal is defined in this way. We are assuming that this is the case. The equation c square, the equation c square gradient of phi square equals to 1, or some people also write it gradient of phi square is equals to 1 over c square is called the iconal equation,
اشتغل.
iconal equation, and can be used to determine the wave fronts given that the wave front
Icon equation.
at some time t equals to 0 is known. So the wave front at initial time is known. This is basically the initial condition to solve this iconal equation. So this is your homework to solve this iconal equation. This is your homework to solve this iconal equation using the method of characteristic. If you will not be able to solve, then please let me know. I can give the solution of this iconal equation. So this is your homework. Next we are coming to the Hamilton-Jacobi equation. So basically like this here. I think I need to start my just so I have given you the one derivation of this iconal equation. There is also a way to derive this iconal equation. I find it easier to derive in this way because just expanding it and then divide. Just when you will be expanding, so one term will be coming as phi x okay, 5x vector, that will be cancelled out and all the terms will be coming with dt. So you will take dt outside and that will be cancelled out and you will be getting this equation. So this was easier when we are in n dimension. This was easier. So we could see that there is also another way to derive this equation. So if you want, then I can give you the another derivation, but for the time being, just solve this equation. It is your homework. Just let me join with this iMac and then I think it will be easier for
Excuse me.
you. Sorry. Yeah. So, so Hamilton-Jacobi equation. I'm not giving the derivation of this Hamilton-Jacobi equation because I am not feeling like that you need to solve this. Just you should have idea what is the Hamilton-Jacobi equation and then it is fine. Because if I am going to give you the derivation, then I need to again define the Hamiltonian function, and I already have defined the Hamiltonian function to order differential equation student, but I don't know about the other students, so I'm not giving the derivation of this. So the initial value value problem given by ut plus Hamiltonian of du comma x equals to 0 in Rn cross 0 to infinite, and we have some initial or boundary conditions, so we don't know. Here I am giving the initial condition. You may see that in all the hyperbolic problem, in all the first order partial differential
Shock
equation,
waves.
we have worked with the uh, initial condition. We haven't worked with the uh, boundary condition. However, for the Laplace equation and for the Poisson equation and even for the heat equation, so we are going to work with the boundary condition there. So it is up to you which kind of initial condition is given. So even sometimes in the case of the shallow water equation, we have the boundary condition at the edges. So where h is the Hamiltonian function, h is Hamiltonian function, and this d of u is basically, if suppose this is n dimension, so del u over del x1 iota plus del u over del x2 j, like I1, I2. Just I am putting this I1, I2 notation to identify the direction, and del u over del x3 iota 3 plus dot 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 del u over del xn iota n. Or there is another way to write the same thing. You can write it like this. So this du is defined as this. So this is the Hamilton-Jacobi equation, is known as the Hamilton-Jacobi equation, and physically it represents an elegant and mathematically sophisticated reformulation. A lot of researchers work on this Hamilton-Jacobi equation because it is also very useful in the optics. So, in the Newtonian mechanics, this is the area where people use it at a very large scale. So, in the Newtonian mechanics, or you can say that it has wide application in optics, mechanics, basically Newtonian mechanics. I'm not going to give you the non-Newtonian and Newtonian. Non-Newtonian means a fluid that has some uh, like glycerine. Glycerin is a non-Newtonian fluid. Lipstick, that is a non-Newtonian fluid. And water, that is a Newtonian fluid. So this is the difference between Newtonian and non-Newtonian fluid, but I'm not going to discuss. When you will be studying, then you may know. So the fluid which does not spread very speedily, like it has some friction in itself, like honey and glycerine and liquid lipstick. So these are non-Newtonian fluid, and the Newtonian mechanics, like you can see the difference. So this Hamilton-Jacobi equation is useful in the Newtonian mechanics. Next, we are coming to the unit 3.
Those are, well, the Newtonian mechanics are the one, uh, the treatment of movement of objects that follows the Newton laws. So,
Sorry,
which,
please.
yeah, the regime where the Newton laws are like applied are like the ones that you can call like Newton mechanics, right? Because
Yeah.
non
I'm not relating it with the Newton's law, because there are more different aspects of those things. Only not Newton law. I am not sure even that I am talking about the Newton's law. So there are many more aspects, because this most important thing which I can feel, that friction, that plays a very important role. Because if as soon as you include a viscous fluid which has viscosity, then your equation is no more first order. As soon as you include the viscosity, that what happens in glycerine and honey and liquid lipstick. So as soon as you have viscosity, here you will include a term of the double derivative del 2u over del x square. That is a more advanced way, like the Navier-Stokes equation I am talking about. So in that case, our system is not first order; it becomes higher order. So it is little bit difficult to discuss those things. Although, as I told you, every nth order linear PDE can be written as system of n first order PDE. Every nth order linear partial differential equation can be written as a system of n first order partial differential equation. And how we can write it, I am going to show you one example. I will show you the example with the wave equation, and I will also give you a very beautiful results how, when the wave equation, that is a second order partial differential equation, when we write it in the system of two first order partial differential equation, in that case we get short wave, and also in that case we get rarefaction wave. And also I told you, if you remember, this was the wave equation, don't you remember? And what I did, I took this operator del over del t plus c del over del x. Now this is a partial derivative with respect to t. This is a partial derivative with respect to x. So one operator is one operator is this, and one operator is this. So the linear combination of two operator is also going to be a operator. So this is a operator, and since this is a differential operator, this is a differential operator, so their linear combination is also a differential operator. Now this is a operator, and when this apply on the equation, so the solution of this, like basically which we get from this will be the solution of this, because this is an operator. And what was this? This was a advection equation. This was transport equation, which was propagating with a constant speed c, is not it? So this is the beauty of the first order partial differential equation, and you can say that if we are given a nth order partial differential equation, then we can write those nth order partial differential equation in the n first order partial differential equation. I am going to give you the example. Actually, I have, and that is even a research paper. So I am going to give you that example, and you can relate those things. But that is the later thing. First, let's see the classification of the second order partial differential equation, because before proceeding anything, we need to know the classification. So I would again ask you, if you are not getting the things very clearly, I will uploaded the notes. So every time when you are in the class, you can open the notes sidewise, because with some students I can feel the difficulty in understanding you, but that is not an issue. If you are not understanding anything, ask me 10 times. I am here to explain. Okay. So classification of second order partial differential equation. Now we have two choices. Either the second order partial differential equation is linear or it is non-linear. So here we are not, I am going to give you the general definition and then we will come into the linear. So the most general linear, the most general linear second order PDE with one dependent variable. Here can you see that we are studying a very simple partial differential equation. We are only choosing one dependent variable. When we will be choosing more than one dependent variable, then it is going to be complicated, is not it? So with only one dependent variable on a domain omega of points, n is greater than 1, n is greater than 1, and for sure at least it is a one dimensional, because t is also there and the space has n dimension. So n is greater than 1, it means at least we have one spatial direction, so that we can say that it is a partial differential equation, because omega is contained in r plus cross rn. So n is greater than 1. So in this way, the second order partial differential equation is defined as uxi uxj plus iota varying from 1 to n bi uxi plus function of u is equals to 0. So if you are going to expand it, then like I'm just giving an explanation. A11 del 2 u over del x square plus a22 del 2 u over del x square, del x1 square del x2 square. If ij is not equal and I is 1, j is 1, so del 2 u over del x1 del x2. So this is just an expansion of this equation. Okay. The classification of PD depends only on the highest order derivatives present. So the classification of PD is PD is motivated by the classification of the, since we are in the second order partial differential equation, so what will be the order of the highest derivative? 2, the del 2 u over del x, like these all are second order, so this is the highest derivative. It doesn't contribute in the classification of the second order PDE. These are the first order non-derivative functions and the source non-homogeneous function. So these terms don't contribute in the classification of the second order PDE. Only the second order terms contribute in the classification of the PDE and how it contributes. So we are very much aware of the quadratic equation of the form ax square bxy plus cy square plus dy plus dy plus 1. So you can see that x and y are two variables. So these are having order 2, x square xy 1 plus 1 y square. So these are having order 2. So a quadratic equation is hyperbolic, elliptic or parabolic according to the discriminant. So if discriminant is positive, then we call it hyperbolic. If the discriminant is 0, so we will be getting the repeated eigenvalues for this quadratic equation. So in that case, it is parabolic. And if this discriminant is 0, less than 0, in that case under root of this will be coming plus minus iota. So we will be getting imaginary eigenvalues, and when for the imaginary eigenvalue, when one appears, then its complex conjugate is going to be there. So for this quadratic equation, one eigenvalue will be a plus iota b. So a minus iota will b will also be there because this is a real equation, real quadratic equation. So in that case, it is going to be elliptic. So this is the classification of the quadratic equation. In the same way, we are going to classify the second order PDE. And the most important thing I would like to mention here, I am going to give the classification only when we have two independent variable, only we have two independent variable, because if we have more than two independent variable, if we have more than two independent variable, so in that case we need to use the canonical form to write it in the, to reduce it to the two independent variables so that we can write in this form. So that is a very long process. So we are here only interested in the case where we have only two independent variables, and even when we are going to solve the Dirichlet problem and Peron equation, so we are going to talk in the one dimension. One dimension. One dimension means one space variable and time variable. So we are interested in only one dimension throughout our Laplace equation. So which is elliptic, parabolic or hyperbolic according as the discriminant is negative, 0 or positive. Thus we have the following second order linear PDE in the two variables. Thus we have the following second order linear PDE to variables x and y. If we are taking only two independent variables, so it will become
Same
a
equation.
del 2 u over del x square. I am just also following the symbolical notation so that you will not be confused. Del 2 u over del x del y. So this is just symbolical notation of those things. So where the coefficient a, b, c may be function of x and y, but for the time being, if it is a function of x and y, then we also need to put some restriction on x and y. But just for the time being, just assume that it is a constant. So the discriminant b square minus 4ac at a point x naught comma y naught. Okay, so I would like to mention one thing. So the value of this discriminant, if we are calculating it as a single at a single point, because we are very interested in constants, so how it will be managed, I am going to tell you. So if it is said that A, B, C are assumed to be smooth functions. So B square minus 4AC is also going to be assumed function. So using that property, if it shows a particular behavior, if it is particularly zero at a point, then it is going to be zero throughout the domain. So that point will be used, that definition will be used, but that is not the matter of fact. You will get to know when you will apply these things, and I don't think you are going to apply it a lot because there are only three equations: wave equation, that is hyperbolic; Laplace equation, uxx and uyy, that is going to be elliptic; and then heat equation, ut minus uxx, that is going to be parabolic. So it will not play a very significant role. So for this equation, b square minus 4c is negative, 0, or positive. We have three possibilities. So when it is negative, we call it elliptic PDE. When it is 0, we call it parabolic PDE. When it is positive, then we call it hyperbolic. It is also related to one thing. So just if we just focus on the geometry, then this is ellipse. So if we are in C, we are in C, so this is I, this is going to be minus I, that is the geometry, and this 0 is
elliptic.
going to be here. If it is parabolic and we are still in C, then it is going to pass through 0 somehow. And if it is hyperbolic, so what is the equation of hyperbola? Either this or rectangular hyperbola is going to be like this. So in both the cases, it will not approach to 0. So this, there is also a geometrical meaning behind this description. I am not telling you in a very broad way because this you might have studied in your undergrad. So this is the thing which is the description. Now I'm going to write some equation. Ut is equals to kuxx. Can anyone tell me it is elliptic, parabolic, or hyperbolic?
Ah, menos b cuadrada
It is elliptic, hyperbolic, or parabolic.
the first is hyperbolic, no? Yes?
Hyperbolic, no. Uh,
No?
A is k, B is 0,
Ah, demonios,
C
sí.
is 0. So B square
Yes,
minus
yes.
4 is 0. So this is parabolic.
Parabolic, parabolic.
Yeah. And what is the definition of this elliptic equation?
Mm, what?
Sorry, I already said that it is elliptic. So here A and this is C. So B square minus 4AC is going to be 0 minus 4. So this is less than 0. So it is, what is the description of this one?
Elliptic.
No, the third one.
The third one, a ver, a ver, déjame, a ver. Let me, a ver, a ver, a ver, a ver. Era menos K. Ah, vale, K. Ay, a ver,
The
tiene que
first
ver.
one is hyperbolic.
Exactly. So when you will pass to the right, UTT minus, because we kept everything here on the one side. So
Maldita sea.
what will be A? A is 1, B is 0, and C is minus C square. So B square minus 4AC is going to be C square. That is positive always. This viscous Burger equation. Can anyone tell me what is the description of this?
Maldita de burger.
If we take this term 0, then it is first order. If it is not 0, then it is second order. So what is the description of this viscous Burger equation? Is it hyperbolic? Is it parabolic? Or it is elliptic?
Oh, A ver,
I don't remember which.
Sorry.
I don't remember which coefficient was related to which partial.
So I am showing this all.
Okay. Yeah. Thanks.
a ver,
Sorry.
mu is a constant or is a
Yeah,
function?
mu is constant. You may take positive and negative according to your, like, let me shift mu equals to c square.
Okay. Will be parabolic?
Yeah, parabolic. So A is mu, B is 0, C is 0. So B square minus 4AC is going to be 0. So it is parabolic. Yeah. So this was the description, and I would suggest you may take a look on more examples defined in your books, like the books I have uploaded. So just go through the books. I am stopping this class here because tomorrow, uh, let me summarize the today class. So what we have studied today: the derivation of the iconal equation. We have studied the derivation of the iconal equation, and then we have gone through the definition of the Hamilton Jacobi equation. We haven't derived this one because it needs the definition of the Hamiltonian and all those things. Then we studied the classification of second order PDE. In the next class, like tomorrow, we are going to see the derivation of Laplace equation. I have made the notes and I am giving the derivation of the Laplace equation and the derivation of the Poisson equation, and then Dirichlet problem,
Dirichlet problem.
and then method of separation of variables to solve the Laplace equation. So today we are going to cover this topic. Uh, I would like to give the derivation, but if you guys are not interested in the derivation of the Laplace equation, so we can skip that part and we can only go through the derivation. Although I have uploaded the notes in which I am mentioning the derivation, so it is up to you. I will ask whether I should clarify the derivation of these two equations, because the derivation is using the Newton's gravitational law, so it is very easier, and I can
I'm
derive.
interested.
Yeah, so it is up to you. You can follow the notes, and if anyone is not understanding the derivation, then for sure tomorrow I can derive, and then we'll proceed with the topic. Okay? Yeah. So if you guys have any doubt, then please ask. Another, I'm stopping this class here, and we can continue tomorrow.
Is this like the solutions of Poisson equation and Poisson equation and Laplace equation has
Mm-hmm.
to do with Lie groups because the generators are like 1/r. Those those like form the solutions form like
Yeah.
kinds of
So I got the.
all kinds of groups, right?
Mm-hmm. Yeah. Please repeat what you are saying.
That the solutions.
Mm-hmm.
Well, I see like the Laplace equation, like in the Schrodinger equation in quantum mechanics.
Mm-hmm.
There's a part that you can like separate, and there's just like the
Yeah, that
Laplace
that
equation.
that's what I'm writing, the separation of variables. And I would also like to tell you tomorrow why we are not using any method and we are using the separation of variables. So there is both way I am going to explain tomorrow, because this problem, the problem of Laplace equation, is not well posed. So we are going to see it tomorrow, but for the time being, just
Yeah.
keep patience and we can discuss it tomorrow, because these topics are very
Okay.
interesting, and it is easier than the unit 2. Unit 3 is easier than unit 2. So everything will be fine because separation of variables is very easy method, what I feel. Okay, so for the time being, I would like to ask you, please go through unit first and two and revise all the topics because your exam is going to be held on 18th of September from 3 to 5 p.m. So it will be of 2 hours, and I think there will be only two questions. So you should clarify yourself all the geometry because I think that unit first and unit two you have studied in a very elaborated way. So it is my expectation that you know each and everything. And if there are some topics that is not clear to you, then we can discuss it on Wednesday. Still, we have 2 days. Is not it?
Yes.
Yeah.
So please revise those topics. And if there are small doubts, silly doubts, please ask. Do ask. Okay. Yeah. So see you tomorrow. Bye.
See you tomorrow. Thanks, teacher. See
Bye.
you.
Bye.
Bye.